Today's topic of discussion is effective nuclear charge. If the charge of the nucleus is Q1 and the charge of the electron is Q2, if we take the valence electron, then the force of attraction between the valence electron and the nuclear charge will be F equal to K Q1 Q2 by R square, where according to Coulomb's law, the F is the attractive force between the two opposite charges and R is the distance between them. We see that the actual attractive force between the nuclear charge and the valence electron is always less than we expected. This is due to the shielding or screening by the inner shell electrons between the nuclear charge and the valence electron. The screening or shielding effect is the effect of reduction of force of attraction by the shells between the nucleus and the valence electron. Due to the screening of inner shells, the actual force of attraction between the two charges is less than the expected force of attraction. Actually, the Z effective is equal to the Z actual minus sigma. Sigma is the screening constant which arises due to the screening of nuclear charge by the inner shell of the electrons. The Z effective depends upon the following factors. Number 1, if the distance between the nuclear charge and the valence electron increases, the screening increases. As a result, the Z effective decreases. If we consider the 1s and 2s electrons, the distance between the nuclear charge and the valence electron for 1s orbital is less than the 2s orbital. So the Z effective for 2s electron is less than the 1s electron because the distance between the nuclear charge and the valence electron in 2s orbital is more than the 1s orbital. Again, we can consider another effect. The diffuse orbitals experience lesser Z effective. That means s orbital have the highest effective nuclear charge value than the p, which have higher Z effective value than the d orbital, and d orbital has the higher Z effective value than the f orbital. We see for s orbital, we see the electrons are uniformly spread over the nucleus, and for 2p or d or f orbitals, the electrons are not uniformly spread over the nucleus. So as a result, for the more diffuse orbitals, the Z effective will be the less. For example, we see that the s orbital are less diffuse, so it has more Z effective. For example, if we take the 4s and 4p orbital, the 4s orbital is less diffuse than the 4p orbital, so the value of Z effective is more than the for 4s orbital than the 4p orbital. If we consider the 3p, 5d and 5s orbitals, if we want to arrange in the decreasing order of their Z effective value, then we see that for 3p orbital, which have the lower n value, it will have the more Z effective value, and in case of 5d and 5s, we see that d orbital is more diffuse than the s orbital. So 5d orbital have Z effective value less than the 5s orbital. As a result, we can say that 3p orbital will have Z effective higher than 5s, and 5s orbital will have Z effective value higher than 5d. To determine the screening constant, we have to use the SLATER'S rule. If Z is the actual nuclear charge of an atom, and Ze is the effective nuclear charge and sigma is the screening constant, then effective nuclear charge Z effective will be equal to the Z minus sigma. The sigma is the screening constant which can be calculated by using the SLATER'S rule. In SLATER'S rule, at first we have to write the electronic configuration of the atom. Then we have to identify the electron of interest and ignore all electrons in higher groups. Now, SLATER'S rule is now broken into two cases for S and p orbital electrons. Electrons within same group shield or screen 0.35. Then electrons within n-1 group shield or screen 0.85. Next, electrons within the n-2 or lower group shield 1.00. That means we can see that if we consider a screening constant for S and p electrons, then the electrons in the nth cell contribute, that means shield 0.35, and electrons in the n-1 cell shield 0.85, and the electrons in n-2 cell contribute to the shielding or screening 1.00. This is for the S and p electrons. And if we consider the D and F electrons, to calculate the screening constant, the nth cell contributes 0.35 and all the other cells contribute to the screening 1.00. Now, to calculate the screening constant experienced by the 2p electron in the nitrogen atom, at first we have to write the electronic configuration like this. Then for one of the valence electron, the screening contributes by the NH electrons will be 4 into 0.35, because one will be the electron for which we have to calculate the screening constant. That means 4 into 0.35. Next, for n-1 cell, that means for 1s2 electron, the contribution towards the screening constant will be, as I mentioned earlier, is 2 into 0.85, because there are 2 electrons in the 1s orbital. The total screening constant value will be 2 into 0.85 plus 4 into 0.35. The result will be 3.10. Now, this will be the value for screening constant. To calculate the effective nuclear charge, the screening constant will be subtracted by the actual nuclear charge. We know that for nitrogen atom, the actual nuclear charge is 7. So, 7 minus 3.10 will be the 3.9. So, 3.9 will be the effective nuclear charge for nitrogen atom. To show the screening constant experienced by a 3d electron, we can consider the bromine atom. Here, from the electronic configuration, we see that the 3d orbital has 10 electrons. From the SLATER rule, we know that electrons within same group shield 0.35 for the D and F orbital electrons, and electrons within the lower group shield 1.00. Here, 4s2 and 4p5 do not contribute towards the screening, because we have to calculate the screening constants experienced by only 3d electron. Therefore, shielding by electrons in nth orbital, that means 3d orbital, is 9 into 0.35, and shielding by all other electrons in the lower group, that means this group contribute 1.00. The total number of electrons in this orbital is 18. That means these are 18 electrons. So these 80 electrons contribute 1.00, which will be 18. The value for scanning constant sigma will be 9 into 0.35 plus 18 into 1, which will be equal to 21.15. Now Z effective value will be 35 because the actual nuclear charge for bromine is 35. 35 minus scanning constant value is 21.15. After subtracting the scanning constants, we get the 13.85, which is the Z effective value for bromine atom. So, in this discussion, I have covered the effective nuclear charge, scanning constant, and the SLATER'S rule for the determination of scanning constant. In my next class or discussion, I will cover the ionization energy and electron affinity. Thank you.